That's all right. Okay, good morning, lads and ladies. Welcome back to Calc 1 Honors. Realize I have a little bit of baby vomit on my shirt. Please don't mind that. Today is going to be a fun day. So your classmate, Nikita, has put together a wonderful collection of videos to lecture on section 3.2, the product and quotient rules. I want to personally thank her for the obvious large amounts of time she sunk into these. It was a real pleasure going over them. So I similarly hope that you guys enjoy them. I'm going to get these queued up for us. Is there anything that you guys would like to ask or talk about before we dive into the material here? Everybody doing good? All right, then here we go. Now let's all pay good attention. Make sure to take nice, clear notes, even though it's a slightly different lecture format, and learn about the product and quotient rules. There will be one point where I stop to insert a little comment. That's it. So here we go. So redirect. And there it is. All right. I'm going to turn off the share and turn it back on because I remember we need to make sure we show sound. Video clip. There it is. All right.
Hello everybody. Okay. So if for whatever reason you can't read the big white letters in the middle of the screen, I'm teaching the product and quotient rule in chapter 3.2, which you will need to remember when I do a bad job of teaching this and you are forced to go to the textbook to find out what the heck I was saying. So remember, chapter 3.2. Okay, the product rule. I'll start with that one. So the basic equation is that, so when you have two functions, f and g, and you need to find the derivative of them, you can't just multiply them together. No, that would be too easy. And one thing that math is not is easy. You have to use this fancy little equation. So f times the derivative of g plus g times the derivative of f. Also, I should mention that this is prime notation, but since math likes to be as complicated and long as possible, especially when it comes to equations, this is technically the formal equation. Now, it is the same equation, it does the same thing, it's just written out. Like the d over dx instead of just the apostrophe, like f of x and g of x are written out more. That's all it is. It's just longer, and because we need that for some reason. But yeah, same equation, same thing. But yeah. Also, f and g must be differentiable. You get it. You can see it. Okay.
So that's the basics, right? If we want to differentiate a product, you have two functions multiplied together and you'd like to take the derivative of that thing. The way you do it is you differentiate the first function, leave the other one alone, multiply those, and then add that to what you get when you leave the first function alone and differentiate the second.
So, example 1, using the product rule. So, find the derivative of f times g of the function v to the third minus 2v times v to the power of negative 4 plus v to the power of negative 2. I'm going to start by identifying each part of the function. So f of v is v to the third minus 2v. G of v is v to the power of minus 4 plus v to the power of minus 2. Okay? And then now we have to find the derivative of each. So the derivative of f, we learned this on Wednesday, of v to the power of n equals n times v to the power of n minus 1. So we have v to the third, so you're going to pull that down here, then subtract the exponent by 1, which becomes 3v squared. Then we have this one, so 2v to the power of 1, pull that down there, then subtract it by 1, so that becomes 2v to the power of 0, or you can just cross that out, and it becomes 2. The derivative of f of v equals 3v squared minus 2. Okay, now the derivative of g, so we have the same idea. So take the v to the negative 4, bring that over, and then subtract it by 1. So that's negative 4v negative 5. Then we have that v to the power of negative 2, and bring it over, subtracted by 1. It is 2v to the power of negative 3. So the derivative of g of v equals negative 4v to the power of negative 5 plus negative 2v to the power of negative 3. Okay, now we can substitute all of those values into their function. So the derivative of f times g is v to the third minus 2v times minus 4v to the power of negative 5 plus negative 2v to the power of negative 3 plus v to the power of negative 4 plus v to the power of negative 2 times 3v squared minus 2. Okay, that becomes negative 4v to the power of negative 2 minus 2v to the power of 0 plus 8v to the power of negative 4 plus 4v to the power of negative 2 plus 3v to the power of negative 2 minus 2v to the power of negative 4 plus 3v to the power of 0 minus 2v to the power of negative 2. Okay, now I'm going to simplify and rewrite. So you can rewrite all the negative exponents as a fraction. So negative 4 divided by v squared minus 2 plus 8 divided by v to the 4 plus 4 divided by v squared plus 3 divided by v squared minus 2 divided by v to the 4th plus 3 minus 2 divided by v squared. Now you can combine like terms, which becomes 1 plus 6 divided by v to the power of 4 plus 1 divided by v squared. And then you can rewrite all of this under the same denominator of v to the power of 4. So that's v to the power of 4 plus 6 plus v squared divided by v to the power of 4. And that is our answer. So the derivative of that function is that. Don't make me say it all again. Okay, example 2.
I do want to pause here for just one moment. So let's take a quick closer look at one other way we could have done this. And this is a theme that's going to come back a little later. So the function we were trying to differentiate is definitely a product. Let me write this down. We want to differentiate. Let's switch over the dot for a second. We want to differentiate v cubed minus 2v times v to the negative 4 plus v to the negative 2. This is a really nice first example because it's actually a problem we could have solved without the product rule. So can anybody tell me how we would have differentiated this if I gave it to you last week?
Do you expand all of it and then use the power rule?
Yeah, exactly. So if I want to, I could have multiplied this out first. And if we do that, I'd have v cubed times v to the negative 4, which is v to the negative 1. Remember, when you're multiplying like bases, you add the exponents. Then my outers would be v cubed times v to the negative 2, which is just plus v to the 1. My inners would be negative 2v times v to the negative 4. That would be minus 2v to the negative 3. And my last terms here would be negative 2v times v to the negative 2. That's negative 2 times v to the negative 1. So using the power rule, we get that the derivative ddv of v to the negative 1 plus v to the 1 minus 2v to the negative 3 minus 2v to the negative 1 is equal to, power rule here, we bring this down and then reduce the power by 1. That would be negative v to the negative 2 plus derivative of v would be 1 times v to the 0, then minus 2, constant multiple comes along for the ride, times negative 3v to the negative 4 from the power rule. And then again, minus 2, constant multiple comes along for the ride, times negative 1v to the negative 2. And then just as Nikita did in her example, we can clean this all up quite a bit. This is negative 1 over v squared. 1 times v to the 0 is just 1. This would be positive 6 over v to the 4. And then this would be plus 2 over v squared. And we can combine the minus 1 over v squared and the plus 2 over v squared and write this as 1 plus 1 over v squared plus 6 over v to the 4, which is one of the forms of the answer that was given in Nikita's video. So I'd just like to point out that some of these problems, you don't need to use the product rule. And Nikita's going to talk about this later when we get into the quotient rule. Certainly, sometimes you also don't need that. Sometimes you can do some algebra and get yourself into a situation where you can use the power rule instead. I don't know about you guys, but I would rather do this. I would rather multiply this out and then use the power rule than have to go through the derivative of this times this plus this times the derivative of this and then do all that simplification. I think this is a good deal simpler. And that's the power of these sort of examples, is to see sometimes you can escape using the nastier differentiation rule by doing some algebra first. And anytime that is an option, you should do it. We're going to see in her next few examples here that that's not always the case. Oftentimes you do need to use the product rule. But if you have some combination of power functions times some other combination of power functions, that's always a situation where you could multiply out and use the power rule. It's not always the most advantageous thing, but it's almost always the best move. So I just wanted to insert that really quickly. I'm going to go back here to Nikita's video.
Again. Okay, example 2. Find the derivative of f times g of the function the square root of x times e to the power of x. Again, I'm going to start by identifying the f and x. So f of x is the square root of x, and g of x is e to the power of x. Okay, move that to the side. Now we have to find the derivative. So this you can rewrite as
Like
x
in car seat form.
to the power of 1/2. Meaning now you can move that over and subtract that by 1, which becomes 1/2 x to the power of negative 1/2. And you can also rewrite that as 1 over 2 square root of x. So the derivative of f of x is 1 divided by 2 times the square root of x. Then we have to find the derivative of e of x, but remember the derivative of e to the power of x is e to the power of x. That one's a hard one to remember, so make sure to write that down. Okay, now we can substitute all of that into our equation. So the derivative of f times g equals the square root of x times e to the x plus e to the x times 1 divided by 2 square root of x. Now we can simplify that a little, and then we can make the denominator equal. So multiply the left side by 2 square root of x, and then you can simplify that. 2 of x times e to the power of x plus e to the power of x. Divide it all by 2 square root of x. And then you can factor out the e of x, and that becomes our final answer. So the derivative of the square root of x times e to the power of x is that. Okay, example 3. Find the derivative of f times g, the tangent line at the point 1, 0, and the double derivative of f times g. So a lot to do in this one. So first, let's just start out by identifying the f and g. So f of x equals 1 plus 2x squared, and g equals x minus x squared. Okay, then we find the derivatives of that. So a constant always goes away. It becomes 0. Okay, this 2x squared, bring that to the front, subtract that by 1, becomes 4x to the power of 1, which is just 4x. So the derivative of f of x is 4x. Now find the derivative of x minus x squared. So this is x to the 1, which is just 1. Okay, and then x squared is 2x. The derivative of g of x equals 1 minus 2x. Okay, now we can substitute all of that into our product rule equation. So the derivative of f times g is 1 plus 2x squared times 1 minus 2x plus x minus x squared times 4x. Okay, now we can multiply all of that out. So that becomes 1 minus 2x plus 2x squared minus 4x to the third plus 4x squared minus 4x to the third. Okay, then you can combine like terms. So that becomes 1 minus 2x plus 6x squared minus 8x to the third. And that is our answer. So the derivative of 1 plus 2x squared times x minus x squared is that. But now we have to do part 2, finding the tangent line at the point 1, 0. So we have our...
Here, we can back up just a little bit. So I don't have timestamp. Oh, there we go. 11:17. Far back do we need to go then? It's 3 minutes. So come back just a few more seconds. So what we're doing here is we're treating this first function as f and the second function as g. We can differentiate each of those using the power rule. The derivative of this guy, 1 plus 2x squared, the 1 differentiates to 0, and 2x squared differentiates to 4x. So f prime is 0 plus 4x, or just 4x. The second guy, x minus x squared, we can also differentiate him with the power rule. The x differentiates to 1, and the x squared differentiates to 2x. So his derivative is going to be 1 minus 2x. Now that we have all 4 of these pieces, f, g, f prime, and g prime, we can plug them into the product rule. This thing we're trying to differentiate is f times g. So that's f times g all primed equals f times g primed. So we'll have 1 plus 2x times 1 minus 2x.
And substitute all of that into our product rule equation. So the derivative of f times g is 1 plus 2x squared times 1 minus 2x plus x minus x squared times 4x.
All right, so we've just plugged each of those 4 pieces into our product rule in the appropriate place. F times g prime plus f prime times g, or sorry, g times f prime. You can write it in either way. So she wrote g times f prime, so g times f prime. All right, I apologize, I didn't catch that meeting in the chat. I can slow it down a little bit, yeah. We'll knock it back to 3/4 speed. Is this everything we need from this guy? Alrighty, I'm gonna go ahead and let it finish.
Okay, now we can multiply all of that out. So that becomes 1 minus 2x plus 2x squared minus 4x to the third plus 4x squared minus 4x to the third. Okay, then you can combine like terms. So that becomes 1 minus 2x plus 6x squared minus 8x to the third. And that is our answer. So the derivative of 1 plus 2x squared times x minus x squared is that. But now we have to do part 2, finding the tangent line at the point 1, 0. So we have our derivative. Now we're going to substitute in 1 to find the slope of the tangent line. So then we can simplify this.
And I'm just going to pause there for a minute. Because we're looking for the tangent line at the point 1, 0, we know the x value there is 1, right? This is an ordered pair, 1, 0. The slope of the tangent line to any curve is the value of the derivative at that x value. So she's taking this derivative we have, and she's going to plug in the x value there, and that's where we're going to get the slope.
This down to -3. Okay, now we can put in our tangent line and substitute our points, and that becomes y equals -3x minus 3.
So the formula she's using here, this is that point slope form, right? And it is really nice to use that instead of mx plus b, because you don't need to go through that nasty procedure of finding the y-intercept. Not that it's a lot of work, but it's nice to reduce your work wherever possible. So remembering this sort of grown-up version of the form of a line is really nice. Just y minus y0, which is going to be the f of 1, the y value on the graph there, equals m times x minus x0. So that formula again, the point slope form of a line. This is passing through the point x0 comma y0 with slope m. Any line passing through this point with this slope has to have equation y minus y0 equals m times x minus x0. It's just a much nicer way to think of linear equations. I know we've all gotten very used to mx plus b, but this is quite liberating in that it frees us from having to worry about what the y-intercept is. It's an affine equation.
Now we can put in our tangent line and substitute our points, and that becomes y equals minus 3x minus 3. Okay, now for our final part, we have to take the derivative. Now this is just a simple derivative. Again, constants go to 0. That just becomes negative 2. That becomes $12x. And that becomes negative 24x squared.
Very good. So taking the derivative again, we use the power rule this time. We didn't need to use the product rule because the first derivative is not a product anymore. This is another example, if you look back at the original statement of the problem, where we could have foiled things out and used the power rule from the start. But I like what we're doing here. It's practice with the product rule. It's very nice. Are there any questions on any of these examples? Okay. So our second derivative, we're able to get from the first derivative. We just differentiate again.
So that is the double derivative.
Oh.
Okay, example 1.
All right, so we have here a proof of the product rule. This proof is not bad. It really isn't. But if you need me to pause at any point, just let me know.
Well, I don't know about the last 3, but I do know how to prove the product rule. Please laugh at my joke.
This is quite cute.
Real and
so how do we know it's true? How do we know anything is true? How do we know anything is real? What if we're all just giant bugs, but we don't know we are because of an intergalactic shield that disguises us, makes us believe we're human when we're really not, and everything isn't real and we're just bugs? Challenging questions. But mathematics is soothing in the sense that we can prove things.
all just bugs, but not really bugs. Well, I don't know about the last 3, but I do know how to prove the product rule. Please laugh at my jokes. Okay, so I'm going to use capital F to signify f of x times g of x. We have the definition of the derivative, the limit as h goes to 0 of capital F of x plus h minus capital F of x divided by h. Now I'm going to substitute in f of x, g of x for it. So the limit of h goes to 0 of f of x plus h times g of x plus h minus f of x times g of x, all divided by h. Okay, now I'm going to subtract and add f of x plus h times g of x in the numerator. Now I'm only doing this because this will help me prove the product rule. So I'm going to substitute it in here. You can see the negative f of x plus h times g of x plus f of x plus h times g of x is there.
So this is a favorite trick of mathematicians, right? When we need terms that we don't have, you can always just add it in, as long as you also subtract it. So the original expression is still here, f of x plus h times g of x plus h, minus f of x times g of x. And in the middle, she's added 0, right? Negative this thing, positive this thing. The middle two terms add up to 0. The reason it's nice to insert those is because then we can group terms and factor out pieces. We're trying to make the derivative of f show up, which we know as f of x plus h minus f of x all over h. And we also want the derivative of g to show up, which is g of x plus h minus g of x all over h. But in order to do that, I need to have terms that I can factor and separate. So this is a very sneaky move that turns out to work really nicely. It's not something obvious, right? It requires a creative step. And this is the creative step, to add and subtract this term. YouTube shit the bed? What are we doing? Come on.
Two different limits. So this becomes the limit of h goes to 0 of f of x plus h times g of x plus h minus f of x plus h times g of x divided by h plus the limit of h goes to 0 of f of x plus h g of x minus f of x g of x divided by h.
So what she's done here is just taken the first two terms, written them as their own fraction over h, and the last two terms, and written them as their own fraction over h. And you'll see why this is useful in just a moment.
Okay, now you can see in the first limit, you can factor out f of x plus h, like that. Now for the second limit, you can factor out g of x, like that. Now, you can substitute 0 for h of this, that, and that. So that just becomes f of x times the limit of h goes to 0 of g of x plus h minus g of x divided by h plus g of x times the limit of h goes to 0 of f of x plus h minus f of x divided all by h.
Implicitly here, we're using the continuity of f. So the fact that f of x plus h on its own, right, we're using limit laws. I'm going to take the limit of this separately from the limit of this. The limit as h goes to 0 of just this f of x plus h piece is equal to f of x because f is continuous. We're assuming here that f and g are both differentiable. And remember, differentiability implies continuity. So this f of x plus h piece, we really can treat it on its own and send h to 0, and he will become f of x. It's subtle, but we're actually requiring that f be continuous there. However, because the hypotheses of the theorem are that both f and g are differentiable, we know that f is continuous.
Now you'll notice that the limit of h goes to 0 of that is just g prime. And the same thing case here, except this is just f prime. So you can simplify the equation to that, and now you get the product rule.
Very nice. It's a lovely proof. And that is the standard proof of the product rule. That is the normal one.
A plane plummets out of the sky.
Sorry.
A speedrunner inexplicably jumps to a higher platform.
What the? Alrighty, so now we're going to start on the quotient rule.
Okay, moving on to the quotient rule. So, for the quotient rule, our basic equation is when you have two functions, f and g, and you need to find the derivative of f divided by g, you can use g times f prime minus f times g prime divided by g squared. And again, long complicated equation. Yeah, you can remember that if you want, but I suggest with the basic equation that I will be doing. Now, an easy way to remember this is to use some like Lodi high trick. It's kind of dumb. Okay, so it's like, let's say that low is like G and high is F, because G is on the bottom in the equation, and so you can think of it like that. And the little thing is low D high, so low as a G, and then D as referring to D divided by D of X. So low D high, or G times the derivative of X minus high D low. What's below? I don't know. That's that's what it is. If that makes sense to you or somehow works. So whole thing, low D high, high D low. What's below? And then yeah. I don't know. That's supposed to help some people. So if it helps you, you can use that.
So this mnemonic,
And
let me share with you a little more on this. It is silly. Certainly it is silly. I'll switch over to the dot cam here in just a second. If you're having trouble remembering how to handle something like this, a lot of people remember it as low times D high minus high times d low over low, low. I think it works because it has a kind of sing-song quality, right? Like low de high, high de low. Kind of sounds like a goofy old 1940s sing-song thing. Low is the downstairs function, and high is the upstairs function. And the D stands for a derivative. Yeah, it is indeed very Mary Poppins. Sounds like something that belongs in a musical from the mid or early 20th century. So low would be G times D high is F prime minus high, which is F, times D low, which is G prime, over low low, or G times G, or G squared. If I'm honest, it's the only way I remember the damn thing. So I don't feel bad if you use this mnemonic. If it doesn't work for you, it doesn't work for you, but for some people it does.
And F and G must be differentiable. I can't say that word still.
Yeah,
Differentiable. Never mind.
All right. So I told Nikita that she doesn't need to prove the quotient rule. The proof of the quotient rule that's offered in the textbook here
Okay.
is not especially satisfying. It's valid, but it is kind of similar to the last proof, the proof of the product rule, in that there's just a lot of symbol juggling. I'll give you guys a much better proof of the quotient rule after we've developed the chain rule. You can think of it as a consequence of the product and chain rules, and that's really the nice way to do it. But it's going to require we cook up something else. So if you want to see the proof as it's given in the textbook, you're welcome to it, but I'm not holding you accountable for that proof. And I don't feel there's anything in there that is insightful or teaches you anything. So it's okay that that is omitted here.
Example 1. Find the derivative of f divided by g of 1 plus 2x divided by 3 minus 4x. So f of x equals 1 plus 2x. G of x equals 3 minus 4x. Okay, now we have to find the derivative. So again, constants always go to 0, and anything with a first degree, only the constant will stay. It just becomes 2. Move that over there. Okay, now the derivative of this, constants go to 0. Thank you. And minus 4 of x, only the constant stays, so that's just minus 4. Okay, now substitute everything into the equation. So the derivative of f divided by g equals 3 minus 4x times 2 minus 1 plus 2x times negative 4, all divided by 3 minus 4x squared. Now you can multiply all that out. Now do not multiply out the denominator. Never multiply out the denominator. Just keep it the way it is. So that becomes 6 minus 8x minus, parentheses, minus 4 minus 8x divided by 3 minus 4x squared. Now you can simplify that. Just that becomes 6 minus 8x plus 4 plus 8 divided by 3 minus 4x squared. Okay, then you can simplify that even further. So that's just 10 divided by 3 minus 4x squared. And that's it. Okay, example 2. Find the derivative of f divided by g of the function x squared plus 1 divided by x to the third minus 1. F of x equals x squared plus 1. G of x equals x to the third minus 1. Move that to the side. Bring down the x squared plus 1. Pull that down. Subtract it. 2x. This becomes 0. 2x. Move that to the side. Move that back up and that down. Okay, now x to the third minus 1. That becomes 3x squared and constant out. So 3x squared. Okay, now we substitute everything into the equation. So the derivative of f divided by g equals f to the third plus 1 times 2x minus x squared plus 1 times 3x squared divided all by x to the third minus 1 squared. Okay, now you can multiply that out, but do not multiply out the what's it called again? The bottom, whatever you call that. So this becomes 2x to the fourth plus 2x minus parentheses 3x to the fourth plus 3x squared, all divided by x to the third minus 1 squared. The denominator, that's what it's called. Okay. Then you can simplify that to minus x to the fourth minus 3x squared plus 2x divided by x to the third minus 1 squared. And then you can factor x out of it, so that becomes that. So the final answer is x times minus x to the third minus 3x plus 2 divided by x to the third minus 1 squared. Okay. Example 3. Find the derivative of f divided by g of that. Now you do want to be careful on this one because it's a bit tricky. You could do the quotient rule. I mean, if you want to, you can. That's fine. But there's a much simpler way to do it. So if at all possible, when you're trying to take the derivative of a quotient, you want to see if you can factor something out. Like notice, x squared minus 4x minus 21 factors into x plus 3 times x minus 7. And you may notice that the x plus 3's cancel out, and look at that. It is now not a quotient. So, and you see how much easier that is? You do not want to use the quotient rule when you can just factor it out. So make sure you don't do all that. Okay, and the derivative of this is just 1. Okay, example 4.
So a quick pause to insert another comment there. The trick that's used here, right, was factoring out the numerator and recognizing that you can cancel the x plus 3. We saw an example in class last Friday where we were able to differentiate a big fraction by splitting it up over its denominator. So it's not just factoring. Any sort of algebra you can do to simplify your quotient before differentiating is wise. If you're very lucky, you'll no longer have a quotient. Even if you do still have a quotient, like if there was another factor down here, canceling the x plus 3 would be nice because you'll have fewer pieces to deal with and overall a smaller expression at the end. So this overarching rule that we've seen in all of our problems so far is that if you can do some algebra to simplify before doing the calculus, you should. Calculus has a way of creating more complex expressions. So if it's possible to simplify the thing you're working with before applying any calculus operations, that's always a wise move. I strongly endorse this. Nikita's exactly right. All right, here we go. The next example, we have x squared e to the x upstairs and x squared plus e to the x downstairs.
Divided by x squared plus e to the x. Okay, f of x equals x squared times.
Before we jump in here, I'd like to point out that you cannot cancel the x squareds, nor can you cancel the e to the x. The top has a factor of x squared and a factor of e to the x, but you cannot factor e to the x out from the bottom because there's no e to the x here. Nor can you factor out x squared because there's no x squared here. So this is kind of like bait, right? I really like the example she chose here because it's very tempting to try and cancel something, but you cannot. So this is an example of a problem where we must use the quotient.
Times e of x, g of x equals x squared plus e to the power of x to the power of x. Take down that. Now you may notice this is a product. So what do we need now? We need the product rule. It's come back. It's made its glorious appearance again. So we're going to do the same thing we did for all the other product rule examples, but I'm just going to call them H and M to make it a little more confusing or less. I'm not really sure what it does, but we're doing that. So h of x equals x squared and m of x equals e to the power of x. Okay, now you have to find the derivative. The derivative of x squared is just 2x. This is just e of x. So, yeah. Okay, now we can substitute this into the product rule function, h and m. So that's all substituted in, I don't know. Okay, so that's x squared times e to the power of x plus e to the power of x times 2x. Now you can factor out an e of x, and that becomes the derivative of f of x. Okay, and then the derivative of g of x, a little more simple, just 2x plus e to the x. Okay. Now we substitute everything into the equation. So the derivative of f divided by g equals x squared plus e to the power of x times e to the power of x times x squared plus 2x minus x squared times e to the power of x times 2x plus e to the power of x, all divided by x squared plus e to the power of x squared. Okay, now we can multiply all that out, and that becomes e to the power of x times x to the power of 4 plus 2x to the power of 3 plus e to the power of x times x squared plus 2x times e to the power of x minus parentheses 2x to the power of 3 e to the power of x plus x squared times e to the power of 2x, all divided by x squared plus e to the power of x squared.
I'm going to pause here just for a second so you guys can follow the algebra. This e to the x is this e to the x. And to get this expression, we've multiplied x squared plus e to the x here by x squared plus 2x here. And then this minus is this minus. Distributing this is easier. X squared e to the x, that's just one term. So you just multiply it by 2x, and you get 2x cubed e to the x. 2x times x being 2x cubed, e to the x come along for the ride. And when you multiply x squared e to the x by this e to the x, you get x squared. And then e to the x times e to the x is e to the 2x. You're multiplying like bases, you add the powers. X plus x is 2x. There's a few ways to proceed from here.
Then you can simplify a bit and multiply all the rest of it out, which becomes e to the power of x times x to the power of 4 plus e to the power of x times 2x to the third plus e to the power of 2x, x to the power of 2 plus 2x times e to the power of 2x minus 2x to the power of 3 times e to the power of x minus x squared times e to the power of 2x, all divided by x squared plus e to the power of x squared. Now we can add up like terms and cross a lot of things out. So that becomes e to the power of x times x to the power of 4 plus 2x times e to the power of 2x divided by x squared plus e to the power of x squared.
So it just happens to be the case that I have a negative 2x cubed e to the x here and a positive 2x cubed e to the x here, right? Writing the e to the x in front or behind does not matter. So these guys, this and this, cancel. Also, this, where is it? The cubic terms yeah, cubic terms cancel, and the quadratic terms cancel. E to the 2xx squared, e to the 2xx squared. Daniel asks, is there an extra x squared plus x at the top here? I don't think so. I think this is correct. So where are we looking? So it would be 3 times f prime. Yeah. Oh, you're thinking of this. So this whole piece right here, see what I'm circling with my mouse now? This is the result of applying the product rule to the numerator. So I'm actually going to run through this in a slightly different notation. I'll show you guys a way I diagram kind of strategically what's going on. But what she has here is correct. This is low. And this is a simplified factored form of d high minus high times d low. So the e to the x times x squared plus 2x, this whole thing is the derivative of the top, because the top required a little product rule. That's where the third term in this expression is coming from. So this is sound, this is correct. I'll show you, I do have a trick for keeping track of these things, and I'll show you in just one moment. But this is a complicated example, so I think it's worthwhile to take a second. Are there any other questions about where these pieces are coming from or going? All right, then I'll go ahead and let this finish, but I will come back to it and show you a way to set these up strategically to help you keep track of where everything is and where everything goes.
Now you can factor out e to the power of x times x. So our final answer is x times e to the power of x times x to the third plus 2x to the power of x divided by x squared plus e to the power of x squared.
So I will pause here for a moment and show you a way to set this up on your paper that is somewhat easy to follow. It's still complicated, of course, and there's no getting around that. But we want to differentiate. I'll switch over in a minute. X squared e to the x divided by x squared plus e to the x. So here's how I would set this up. I would say d dx of this thing, x squared e to the x divided by x squared plus e to the x. I like to use the prime notation. So we know this is going to be low d high minus high d low over low low. So that's x squared plus e to the x times x squared e to the x primed. So this prime is attached just to this piece, and then minus high d low. So that's x squared e to the x times x squared plus e to the x primed. All of that is down divided by x squared plus e to the x quantity squared. So I find by kind of setting it up like this first, where I haven't taken either of these derivatives yet, is a really helpful roadmap. It kind of tells me what it is I'm gonna do next without giving me too much to do in one step. So in this single step, all I've done is implement the quotient rule. All I've done is written down what the formula for the quotient rule says I should have. Now I'm free to take a minute and think about what is this derivative and what is this derivative. You can do it off to the side. So I can say, okay, now x squared times e to the x, all primed. That's a product rule thing. So this is going to be, I differentiate the one and I leave the other alone. That's 2x e to the x plus, I leave x squared alone and differentiate e to the x. That's x squared e to the x. The other place I needed a derivative was here. And these are being added. There's no need for a product rule. So this is going to be 2x plus e to the x. And then I can take these pieces and plug them in. And you'll see x squared plus e to the x times. Now what she did is factored out this e to the x, right? Here, this piece is e to the x times 2x plus x squared. So here goes e to the x times 2x plus x squared minus x squared e to the x times 2x plus e to the x. And all of this goes over the square of x squared plus e to the x. And I really like what Nikita is saying about please don't FOIL this out. You don't need to do it. It never helps. Really doesn't ever help. Leave that as that quantity squared. Factoring this e to the x at this step, it's not necessary. You could plug that in as this. So in place of these, you could write just this instead. But the long-term goal here is going to be factoring, right? We want to factor the top and bottom just as much as we can. So there's no harm in factoring this e to the x out at this step here, and then plugging that in. And that's where that extra 2x plus x squared piece was coming from. Looked like we had a third term, but we didn't. She just factored the d high portion of the low d high d low. All right, very nicely done.
Okay, the end. Or is it? Example 5. Find the derivative of f divided by g of 1 divided by x plus e to the power of sine of x times cosine of x plus x to the power of -3 all multiplied by 13x squared plus 2 to the power of x divided by the square root of x squared plus 1 plus ln of x plus e times sine of x plus 1 divided by x to the third, all divided by 26x plus ln x times the square root of x squared plus 1. So first, no, I'm just kidding. It's the end. Thank you for watching. Not like you had much choice. Well, I mean, you could have just not come to class today, or just not paid attention, or I don't know where I was going with that. Okay. Anyway. Bye.
Alrighty, so this is very nicely done, and I definitely want to thank Nikita for the obvious large amounts of work she put into creating these videos. Truly wonderful stuff. Before we move on, are there any content questions? Any questions about any of the examples or the rules that we'd like to look at a little more closely? Yeah, I have to agree. Genuinely amazing. One of the nicest student lectures I've seen ever teaching here at Santa Fe. The level of polish there is really fantastic. And if anybody is curious about how she was able to make those animations or the really nice video, I am curious as well. So I'm familiar with PyMath and a few other things to animate at that level, but it usually requires some coding skill and quite a lot. So can I ask you, Nikita, what did you use to make that? Just PowerPoint? Wow. That must have been some real work then. I imagine that took some time to get all the animations and uncovering in. Good, good. That's definitely the goal. The goal is that by taking the time to do this stuff, you develop a depth of understanding that is special. Definitely very impressive. Really, really nicely done. I love the examples you chose and the way that you put it together into the PowerPoint with the animations and the uncovering. Very, very nice. Are there any questions for Nikita or for me about the product and quotient rules themselves? Lovely. Alrighty then. One thing that we did see in that last example is that it is possible for a product rule to show up within a quotient rule. Those sort of things are not uncommon. And as we learn more of these differentiation rules, you will see one or two showing up inside of another one from time to time. And you want to make sure to handle those very carefully. The big take homes there, the things that people tend to err on or get themselves in trouble with. Simplify using algebra before you do the calculus. Anytime that's possible, you want to do that. Now you need to do it correctly, right? Like we said here, you cannot cancel the x squareds or the e to the x's. Make sure you're doing the algebra correctly, otherwise you're dead in the water, but do algebra before calculus. And then I really liked what she said. It's not something that I've said in my lectures in the past, but I really like it because it's certainly true. This squared term downstairs in the quotient rule, I cannot think of a single case where multiplying this out makes life easier or better or does anything good. Generally, our goal is to factor and cancel as much as we can. So multiplying these terms out from the downstairs of the quotient rule, that square, is almost always not just not helpful, it's almost always a step in the wrong direction. So if you have something like this, leave it like this. If it's in the downstairs and it's looking like that, leave it like that. There's no need to multiply these sorts of things out in the denominator, because our hope, if anything, is that we'll be able to cancel one of those factors, and we know we need things factored in order to cancel. I think that is every little bit of stuff we could possibly want to cover today. So let's again thank Nikita for the very large amount of time I'm sure she invested in that wonderful, wonderful lecture. There will be a new homework opening up for you guys today, and your test is around the corner. We are getting close. We said after we finish the chain rule, we'll be ready for the test. I know I said I would have the early version of your study guide up, but I got wrapped up in meetings last Friday. I haven't had the time to do that, so I'll get that up this afternoon. If there is anything else that you guys need, I have an office hour today from 1 to 2 p.m. You can talk to each other on the Discord, or you can send me a Canvas message. That is it from me. I will see you guys on Wednesday. Yes, very, very nice.